In this video, we will be continuing on our discussion of the development of the modern atomic theory as a way to illustrate the scientific method in use. In this video, we will be talking about how electrons were originally discovered. J.J. Thomson, an English chemist, performed a series of cathode ray experiments, and it was observed that in these cathode rays, a beam of particles, which were later determined to be electrons, at the time called cathode rays, traveled from the negatively charged electrode, called the cathode, to the positively charged one, which was labeled the anode. The electrons that compose a cathode ray had the following properties. They traveled in straight lines. They are independent of the composition of the material from which they originate. The way that Thomson tested this, or came up with this observation, was on the cathode, the negative electrode, he changed out the material. So in some cases, using things like a copper electrode, a silver electrode, a gold electrode, various metals, each one gave the same beam of cathode rays, later to be called electrons. The cathode ray beam was determined to have a negative electrical charge, as we will talk about in just a second. J.J. Thomson was able to measure the charge to mass ratio of the cathode ray particles by deflecting them using electric and magnetic fields, as we will see in the next slide. The value that he measured was negative 1.76 times 10 to the third coulombs per gram of the cathode rays. What a cathode ray is, in terms of the original Thomson experiment, is a long glass tube that typically they evacuate out the gas so that there's very little, if any, gas particles still in it. Then you have your cathode, you have your anode, and you put an electric current through the gaseous vapor, right? So you apply an electric current between the cathode and the anode, and what they find is that at the cathode, this beam of particles are coming out. So the cathode's over here, your beam of particles. In order to restrict the ray, there was a cylindrical disc with a small hole put in it to block most of the rays, which confined the actual ray itself to a very small diameter that they could then work with in experiments. This went through another disc with a small hole on it to the anode. So what they found, or what Thomson found, was that the ray went into a straight line, but when you apply a magnetic field to it, you can deflect the beam either up or down depending on the end of the magnet that you're interacting it with. So the beam itself would be pulled towards the positive side, towards the plus end of a magnet. He also found that he could deflect it by having an electric current, which we now know creates an electromagnetic field, and get it to bend the ray either up or down. Old televisions, called cathode ray tubes, use this same principle. So they have a cathode and an anode. The anode has a hole in it, so the beams are pulled or are ejected from the cathode towards the anode, and then they go past the anode. Then you have a magnetic field which can then be used to point the beam to wherever you want on the tube, causing it to light up. So if you take one of the old heavy cathode ray tube televisions, you can see here is your cathode, your anode, your magnetic field, and then based on the strength of the magnetic field, you can get the cathode ray to bend left, right, up, or down, because you have two series of magnets, one above and below, and one to the left and right. You can get the cathode ray to bend to wherever on the screen that you want. It strikes the phosphorus, or the phosphorescent dye that's on the television, causing it to light up the various different colors. Because the cathode ray is deflected by both a magnetic and electric field, Thomson believed that the cathode rays themselves had a charge. And in fact, because of how they were deflected, he knew that it had a negative charge. The way that he summarized that there was a negative charge to these particles was based on the properties of electrical charge. When you have two different charged particles, if they are opposite in sign, they will be attracted to each other. So if you have a positive charged particle and a negative charged particle, they are attracted to each other. If, on the other hand, you have same charges, they will repel each other. So a plus will repel a plus, and a minus will repel a minus. So because the rays themselves were deflected up or down depending on the charge that was put near them, Thomson was able to determine that the beam, which we now know are electrons, had a charge to them. If you have two charges, a plus and a minus, they will cancel each other out in terms of the sum of the charges, right? So if you have a plus 1 and a minus 1, then altogether you have a 0. So positive and negative charges themselves will be of the same magnitude and sum to 0 when combined. From the cathode ray experiment, Thomson knew the charge to mass ratio, but from that, it's just the ratio. He didn't know the charge or the mass of the particles. He just knew what happens if you take the charge and you divide it by the mass. It wasn't until Robert Millikan did his Millikan oil drop experiment that the charge of an electron was determined. And because from Thomson's experiment, you know the ratio of charge over mass, if you can determine either the mass or the charge, you can get the other value. So the Millikan oil drop experiment, which we will go into in just a second, was able to determine the charge on an electron. And because Thomson knew the charge to mass ratio, he was able to determine the mass given the charge. So the oil drop experiment done by physicist Robert Millikan was used to determine the charge on a single electron. The way the experimental setup works is Millikan had an oil in a perfume dispenser with an atomizer. So this part here was essentially just a perfume dispenser. The oil itself, when the atomizer was depressed, would shoot out and create fine droplets. The contraption itself had a positively charged plate and a negatively charged plate. On the positively charged plate, there was a small hole which would enable individual droplets to come down through. Right, so the atomizer pushes the oil out, the oil sprays out in fine droplets, and then because there's only a small hole, only a couple droplets actually are able to make it through the hole. They will drop down, and then you have ionizing radiation. So this is high energy radiation which will push an electron onto the droplets. Then perpendicular to that, you have a light source which enabled the viewer, the person viewing it, to be able to see the droplets. By playing around with the charge on the positive and negative plate, Millikan was able to get the charged particles, the oil drops that had captured one or more electrons, to hover in place. Right? So the force of gravity was counterbalanced by the repulsive force between the negatively charged plate and the negatively charged oil drops, which had accepted an electron from the ionizing radiation. So when Millikan looked through the viewing microscope, he was able to determine the radius of the oil drop. And because he knew the density of the oil drop, he was able to determine the mass of the oil drop. Knowing the mass of the oil drop and the charge that's needed to hold it in place, he was able to figure out the force that was being exerted to counterbalance gravity. From that, he was able to determine the charge of the oil drop being suspended. So because the ionizing radiation would impart whole numbered values of electrons into the oil drop, typically 1, 2, or 3, by looking through the viewing port, he was able to determine the mass of the particle and from that infer the charge that the oil drop had picked up. This enabled Millikan to calculate the charge on each drop and was determined that the charge was negative 1.60 times 10 to the negative 19th coulombs per drop of oil. This corresponds to the charge on an electron. From that, you could then use the ratio from the Thomson experiment using the cathode rays to determine the mass of an electron.